From the Library of Congress in Washington, D.C.
Hi, I'm Stephanie Marcus from the Science, Technology, and Business Division at the Library of Congress. I want to welcome you to the 9th year of our collaboration between my division here at the library and NASA Goddard. And we've really enjoyed this over the years, and we look forward to many more. This is the first of 7 lectures this year. We got kind of a late start, but so did everything else, the flowers, whatever. And so we have another one coming up June 11th, and that one is going to be on, it's a space weather topic. I cannot pronounce the mission, but it launched just back in March, so fresh data. The speaker today is Paul Newman, who is Chief Scientist for Atmospheric Sciences in the Earth Sciences Division at Goddard. He's also a co-chair of the Scientific Assessment Panel to the Montreal Protocol on Substances that Deplete the Ozone Layer, lovingly known as the Montreal Protocol, and regarded as one of the most important global treaties in history. The Scientific Assessment Panel is tasked with writing a report every 4 years on the state of ozone depletion. Dr. Newman is originally from Seattle, so he knows weather, and he attended Seattle University there and earned a BS in physics with a minor in mathematics. His doctorate in physics is from Iowa State University. He came to NASA Goddard in 1984 as a postdoc researcher and officially became a scientist there in 1990. His principal area of research is stratospheric dynamics and chemistry. That's probably the easiest way I could put it, because I've seen other technical writing about what he does, which I cannot understand. He has authored or co-authored more than 130 scientific papers and reports. Among his many projects, Dr. Newman manages NASA's Ozone Watch page, and that provides the latest status of the ozone layer over the Antarctic, with a focus on the ozone hole. If you want to just Google it, you can put in Ozone Watch and find the page. Just a couple of days ago, BBC News reported that the Antarctic ozone hole would have been 40% bigger by now if it were not for the Montreal Protocol. There would also have been a hole over the Arctic, which would have affected northern Europe and fried up those sensitive pale skins. There's much more to be said about Dr. Newman, but I think it better to bring him to the podium to star in A World Avoided: How Science and Policy Solve the Global Ozone Crisis. Dr. Newman.
Thank you, Stephanie. So first, you're probably all wondering, am I related to the actor? We are here in the Mary Pickford Theater. The answer is no. But please buy all of my products, the salad dressing, the popcorn.
The ozone dressing.
The ozone dressing. So what I'm going to do is I'm going to go through a little story here. I'm going to tell you a story about how a great chemical was invented, chemicals, chlorofluorocarbons. And then they were found to have a pretty bad effect on the ozone layer. And that's important because ozone is the Earth's natural sunscreen. So if the ozone layer is depleted, it has a rather bad effect on the Earth's surface. And I'll show you some of that. I have one little dramatic movie I think you'll all like. A lot of this work is from a vast number of scientists. I can't even begin to list all the people who have made contributions that have gone into this presentation. I start off with a picture here you can see in the background here. This is called the polar stratospheric cloud. And this is one of the key elements behind the ozone hole. And this was really a dramatic impact on our understanding of the chemistry of the stratosphere. These are incredibly beautiful clouds that you see. They really do have this opalescent color to them. And they're just amazing to see. But these have a very deadly impact on ozone in the Arctic and in the Antarctic. So let me start off by giving you a few ozone and UV basics. First of all, let me tell you where the ozone layer is. The lowest layer of the atmosphere, the bottom one you see here, is called the troposphere. Maybe 10% of the ozone is in the troposphere. The bulk of the ozone layer is up in the stratosphere. So most gases, they decrease as you go up in altitude. That's why you have a hard time breathing on the top of Mount Everest. But ozone actually is one of these gases that increases with altitude. So 90% of the ozone there, and it's a 3-oxygen atom molecule. Most of the ozone is found in the stratosphere. The mesosphere, the layer above the stratosphere, has a little bit of ozone, and the thermosphere has even a lower amount of ozone. Now, ozone is important because it's the Earth's natural sunscreen, and I'll get into a little more detail on that. So now I'm going to show you a plot of how much ozone there is, and I'm going to show it in terms of parts per million. So this is if you take 1 million molecules, how many of them are ozone? And you can see from the numbers there, not many. You go up to an altitude of around 25 miles or so, and only about, on average, about 8 of those molecules are ozone molecules. There are not many ozone molecules in our atmosphere. I'll show you another part of that too. Now, ozone, it doesn't absorb in the visible. You go outside, ozone doesn't do anything to visible radiation. There's a kind of radiation called UVA. If you ever look at your bottles of sunscreen, you'll see screens UVA, screens UVB, and they don't say anything about UVC. And I'll show you why, actually. UVB, 90% of the UVB is absorbed by ozone, 90% of it. So it is really the important UV radiation. Now, one thing I should say is that UV radiation is a bad form of radiation because it can break apart biologically active molecules. So things like DNA can be broken down and damaged by UV radiation. And that's why you get things like skin cancer. I'll actually show you a little bit of that. Now, they never talk about UVC because UVC is absolutely absorbed by ozone. I once did a calculation on UVC, and these are wavelengths less than 280 nanometers. You go down to 260 nanometers, you see a photon, one photon from the sun get to the Earth's surface in the UVC about every 1,000,000 years. It is absolutely, if your eye only could see in the UVC and not in the visible, the world would be completely black to you. So ozone is incredibly efficient at getting rid of UVC, somewhat pretty efficient at UVB, not so efficient at UVA. And so when we talk about sunscreens, be sure they screen UVA and UVB. Also, make sure your sunglasses actually screen UV. A lot of them don't say it anymore, but in the past, sunglasses didn't screen UV. Your eyes would open up and you get more UV radiation into your eyes. So, okay. Now, I mentioned that there's not a lot of ozone in our atmosphere, and I'm just going to show you, here's a little satellite, and it measures ozone. We typically measure in what's called the Dobson unit, okay? And the Dobson, I'll give you an idea what a Dobson unit is. If you could take all of the ozone above us, all the way to space, and you could bring it all the way down to the Earth's surface at standard temperature and pressure, so about freezing or so, that layer of ozone would be 3 millimeters thick, okay? And to give you an idea what 3 millimeters is, 2 pennies stacked on top of one another is 3 millimeters thick. That's how thick the ozone layer is. Yet, if there was no ozone, life on the Earth's surface would not be possible. And I'll show you a quick example of that. This is what you do if you take a plant and you increase the amount of UV that the plant is exposed to. You get these little stems on the left. If you decrease the amount of UV, you get the little stems on the right. They grow better if there's less UV. And that's because these plants are actually, they have defense mechanisms, but if they're expending all of their energy to repair themselves from UV damage, they grow less efficiently. That's the bottom line on UV. So now I want to show you a relatively dramatic demonstration I did a couple of years back in 2011, in which at Goddard we launched satellites, and so we have to test materials to UV exposure in outer space. And so we have what is called a solar simulator. In the middle, you see that big tannish box, that's a solar simulator lamp. And that simulates the full sun spectrum, including all of the UV that is screened by ozone. Now I've got a little camera there on the right. I mounted it and I did a time-lapse shot. And then you can see in the bottom right, there's a little boxwood basil plant. And so what I did is I turned on the lamp and then came back the next day and turned off the lamp. And then I watched the plant evolve a little bit to see what would happen to the plant after a couple of days. So now I'm going to show you what happens. So there's the plant, and it's exposed to UV. And you can see that this is every 10 minutes. Now it changed color there because I turned off the lamp, but I kept photographing the plant. And so you can see that some of the leaves in the background were kind of screened from the direct beam of the solar simulator. And the ones in the front, they look like they're all dried up and curled, but they're actually kind of tactile to your sensation there. So they're not dried up. They're actually the brownish. There's a lot of you actually are taking all the photosynthetic process and you're just destroying it. You're creating a lot of toxins in the plant. Now, the last thing about this, I had a couple of control plants. I took them out of the lab, put them off into a place. We have a little break room there, and I kept them watered. And I was looking at the control plants, and they all thrived. They kept growing and everything. This one absolutely died, even though I was watering it and put it into regular sunlight behind glass, so it was getting no UV. And so it was actually the toxins that were produced from the UV that actually killed the plant fully. So not only does the UV directly damage the plant by destroying its biological molecules, but you produce all these toxins in the plant which then kill it absolutely. So the plant died after a couple of days. So this is not so, you can't really never have an ozone layer. This is just an example of if you didn't have an ozone layer, you really do kill everything on the Earth's surface. And in fact, life on the Earth's surface didn't evolve until the ozone layer developed, if you go back through the history of the ozone layer. So now I'm going to talk a little bit about stratospheric chlorine chemistry. And the first thing I want to show, and I want to highlight some people. I think there's some real heroes in this whole story, people who really carried the ball for many years on a topic that was very controversial. The first person on the right, these are two guys. On the left is Rich Stolarski. Rich worked many years with me at NASA Goddard. And on the right is Ralph Cicerone. Ralph was a professor at University of California for many years. He is now the head of the National Academy. And so they published a paper, Stratospheric Chlorine, a possible sink for ozone, which they pointed out that a chlorine atom could catalytically destroy ozone. And what I mean by catalytic, it means the chlorine atom would destroy ozone and regenerate itself and destroy another, and regenerate itself and destroy a third and regenerate. And so on average, one chlorine molecule in the stratosphere could destroy a couple of thousand ozone molecules. So chlorine is a very efficient destroyer of ozone. Now, this is a very interesting paper, but then it was followed very shortly by a second paper by Mario Molina here on the left with the beard, and Sherry Rowland or F. Sherwood Rowland on the right there. And they did this paper, Stratospheric Sink for Chloromethanes, and they meant chlorofluorocarbons. We called them chloromethanes. That's what they are, but we call them now chlorofluorocarbons. And they pointed out that the CFCs were accumulating in our atmosphere, and the only sink for these chlorofluorocarbons was if they got into the stratosphere, were broken down when they got above the ozone layer, exposed to intense UV radiation and releasing chlorine. So they were pointing out, this is the paper in 1974 that said chlorofluorocarbons are a direct threat to the atmospheric ozone layer. And I'll just to tell you the end of the story about these two guys, they won the Nobel Prize in 1995 for this work. But that was after many years of when this paper first came out. You can imagine there's a huge industry looking at chlorofluorocarbons, producing them. And in fact, Mario and Sherry had to put up with a lot of attacks on what they were doing. But they, in the end, were shown to be right. So the basic theory is that you start off with chlorofluorocarbons. That leads to ozone depletion. and that leads to increased UV. Now let me say a word or two about these chlorofluorocarbons. Now, I think you all remember in the past we used to use hairsprays back in the 1970s. It was used in spray cans, so it was used quite extensively, but it's also used in refrigeration units and in air conditionings. So CFCs were very, very prevalent back in the 50s and 60s. On the left, I want to show some fire extinguishers because they contain a class of gases called halons. And halons contain bromine. Bromine is chemically similar to chlorine. It's one of the halogens. But bromine is actually much more efficient at ozone destruction than chlorine, about 60 times more efficient. So if one chlorine molecule can destroy a couple of thousand ozone molecules, one bromine atom can destroy about 100,000. So it's much more efficient. And then on the right, I show a little a foam cup. They used to use CFCs as a foam blowing agent. And in fact, in many buildings, you'll find the insulation in these buildings, the foam insulation was produced with chlorofluorocarbons. So there's a lot of CFCs that are still around us in these buildings. And if you tear down the building, you release these CFCs. So these were the compounds, and they were actually wonderful chemicals because they're non-explosive, they're non-toxic, they're really wonderful. And in '74, Molina and Rowland showed that these things could destroy the ozone layer. So in fact, they did have an impact. You have to worry about gases. If you take a gas and I was to release it here, you kind of wonder, where does it wind up? And what does it do on its pathway through the atmosphere? Does it get into our lungs and hurt us? Does it just float around in the atmosphere and does something? Is it destroyed inertly? We don't know with a lot of these gases that we've created. And this was a case where we found out that, well, maybe this one is really destructive for the ozone layer. So by 1979, there were a lot of people who were modeling ozone, and these were three scenarios in 1979 with a very crude model that showed if you began to regulate it, state one, in 1975, the release rate was fixed, and after 2000, there was no more release, and it fell off very slowly. In 2, the 75 release rate was just fixed, but it kept going up because you're releasing the same amount every time, and these gases all have very long lifetimes. The lifetime of CFC-12, which was used in car air conditioners, has a lifetime of a little over 100 years. And then in 3, it's just you kept increasing. Okay, the business as usual. No changes in regulations. So these were what the models were producing in 1979, and so people these were including more chemistry, more physics. So people were really starting to get nervous in the late 70s and early 80s. Now, scientists really got their acts together. We began to write reports on what was going on with stratospheric ozone, and this was a report that was published in 1985, and if you actually look at it, it is produced by 150 scientists from 11 different countries. The United States featured very prominently in that, and it ran to 1,094 pages, not including references. I should mention to the librarians that the 1,094 is not references. But if you include the references, it's probably, I don't know, 1,300 pages. And you can see a copy of this is out there on the stands. So it was very good inclusion there. So now people began to get worried about it. Policymakers began to see that, okay, the scientists are really getting their act together, and we've quite evolved from 1974. They're saying that we're really going to have a lot of ozone depletion. Now again, those were pretty crude models, but we're looking at a lot of ozone measurements. We're looking at a lot of chemistry in the lab. So things were starting to solidify, and that's why you get a report that's 1,094 pages. So regulatory actions began to develop. So in 1974, Molina and Rowland published their paper. In 1975, the United Nations Environmental Program, the Governing Council, backed a program of research. Now, the United States had a pretty good research program running at that time, and it got even better with time. By 1977, there was an international meeting, and they devised the World Plan of Action. By 81, they'd already started to talk about regulating CFCs. They were looking at that plot that I showed you that showed ozone depletion getting worse and worse and worse. So they began to worry about it in a big way. Now, getting countries to agree on something, as we've seen with climate negotiations, is actually quite difficult. But we'll get on to that. So that book I just showed you, it was published in 85. And based on that book, the Vienna Convention for the Protection of the Ozone Layer was negotiated. Now, this is actually a really nice little agreement because it recognized that there was a problem. The countries of the world now recognize there's a problem and we have to deal with it. Okay? It established kind of framework in the Ozone Secretariat, which is part of UNEP, and there was going to be regular meetings on ozone layer issues. And it actually established a scientific framework for research. So the internet countries collaborate on ozone research now because of the Vienna Convention. So that's kind of the overarching agreement to everything. It didn't do any regulations, though. I should point that out. So in 1985, this was the real earth-shattering result. Now, we'd been predicting that there would be ozone depletion. We didn't think it was going to happen this fast. This was really shocking to the stratospheric community to see this plot. And it's these three gentlemen on the right. On the left side here in front is Joe Farman, and standing in the middle there is Brian Gardner, and on the right is Jonathan Shanklin. And they're standing in front of a little instrument called the Dobson spectrophotometer that measures the ozone amount above you, the total amount of ozone above you. And this is, I mentioned the Dobson units. Remember, 3 millimeters down at the surface is 300 Dobson units. So they're showing that ozone declined from somewhere around 300 Dobson units up here as you went from the late 50s, and it had plunged down here to less than 200 Dobson units by 1984. This was a real shock because this instrument cannot be that wrong. This is a very solid instrument. The error bars on this instrument are probably the width of the dot. And so the scientists looked at this and they're flabbergasted, frankly. And I think I had just arrived at Goddard, and I'm looking at plots like this, and actually you lose a little sleep about stuff like this. Why is this happening? We don't know. And so there was, at NASA, we have satellites that measure total ozone. And in fact, these were the same measurements we were getting from our satellite. And whereas they're measuring over Halley Bay Station down there in Antarctica, that's what the black darts are. These are actually, if we looked at the October average, what the minimum value would be. So they're a little bit lower from the satellite because of the way we're looking at the data. And in fact, at the same time that Joe Farman and Brian Gardner and John Shanklin were publishing their paper, there was this guy down here, P.K. Bartia, and he's another one of my NASA Goddard colleagues. He made this map. Okay? This is the first ozone hole image, and it was published in 1985. And you can see where you look at these blue colors, that's high ozone, and here, that's very low ozone, this dramatic red. Now, Sherry Rowland, the guy, I think, this is actually the story about the naming of the ozone hole. He looked at him and he said, oh my gosh, it looks like there's a hole in the ozone layer. And that's how the name, the ozone hole, came up. Now, this isn't truly an ozone hole because there's still some ozone above you. Remember, this is down below 200, but it isn't zero, okay? So ozone hole is a little bit of a misnomer, but you can see from the picture why you would say that. This picture actually appeared in the New York Times. And so now there's kind of not only we're worried, the policymakers are worried about ozone, but there's this dramatic decrease. It's kind of continental in scale. It's a very large phenomena. And what does this mean? Is this going to happen? Everybody's asking the question. Will this happen in other parts of the world? Is there some unique conditions over Antarctica? So this was really sort of a backdrop to all of the negotiations that were going on. So I just wanted to mention that actually appeared in that blue book, Atmospheric Ozone, 1985, also. So just to give you an idea, there's a modern picture of the ozone hole, and you can see I superimposed the U.S. on the Antarctic continent, kind of give you an idea of scale. It's a big thing down there. It's a lot of very large-scale depletion. And so there was a lot of research coming out of that. Here's an article from the Washington Post from 1989 talking about the radiation increases, UV radiation surface increases. So already were making all these connections. One thing I didn't mention that is in 1987, we flew a U-2. NASA has two civilian versions of the U-2, and we flew over Antarctica with this U-2, and we measured chlorine levels that were astronomically high compared to what was expected, and ozone that was very low, just like we were seeing from the satellites. So we put the whole puzzle together. There are a lot of CFCs, there's a lot of ozone depletion, and there's a lot of UV at the surface. Okay, so just to kind of give you the science is really starting to get its act together at this time. And there was a lot of stories coming out about ozone depletion. So the media was really starting to pay attention to it also. Became a fairly big topic. And some of us who were back there at the time, it was almost every day or every other day there'd be another article somewhere in the Post or the Times or the LA Times about ozone. It was really a big hot topic because nobody really knew what was going on. Okay? So the backdrop to all that was there was that big blue book, all these scientific results. And what that did is it resulted in the Montreal Protocol being negotiated in 1987. And it was signed by Ronald Reagan shortly after it was negotiated. But it did, as opposed to the Vienna Convention that identified that there was a problem, the Montreal Protocol actually established regulations. So it regulated the production and consumption of specific substances that modify the ozone layer, okay? And that included chlorofluorocarbons. So that's great. It has another couple of mechanisms in it. It has a multilateral fund, and this is a pot of money that is used to help countries reduce their usage of ozone depleting substances. It established regular reporting of production and consumption, so chemical companies have to tell their governments what they're doing. The governments then report it up to UNEP, and we scientists can we can look at how chemicals are changing the atmosphere and decide, oh, were those production numbers right or wrong? Is that consistent with what the companies are telling us? And it has an assessment process. So every 4 years, we write a scientific assessment. There's a technology and economics assessment panel, and there's an environmental effects assessment panel. And under the Montreal Protocol, this is my second, I have my primary job at NASA, but my second job is with the scientific assessment panel. So now, one of the other things that I didn't tell you was that the Montreal Protocol is actually an evolutionary agreement. It can be amended. And in fact, there have been a number of amendments that have strengthened the Montreal Protocol. So here's the Vienna Convention, here's the Montreal Protocol. There was a London Amendment in 1990, a Copenhagen Amendment, a Beijing Amendment. So this is one of the meetings, this is in Doha, and this is me sitting in the very back. Me and my this is Mike Carrillo. Mike was a program manager down at NASA for many years, and he is the chair of the Ozone Research Managers. But see all the countries sitting up here, and they always put the scientists in the back of the bus. It's like the unruly students are put into the back of the class. Same thing. Okay, so I told you that ozone depleting substances were regulated. They were increasing with time. The Montreal Protocol was signed in 1987, and they've been going down. Now, what would have happened if there had been no Montreal Protocol? Well, this is just a simple growth rate here. This is an increase of 3% every year, entirely consistent with what we were seeing in the 60s and 70s. In fact, there are even greater growth rates back in here. But 3% is a fairly conservative approach to how chlorofluorocarbons would increase. So we call that the no Montreal Protocol. So what did the Montreal Protocol actually do? The Montreal Protocol itself did not stop the growth of CFCs. It slowed it, okay? So it was going up less fast. The next amendment was the London Amendment. It slowed it even more. And then the Copenhagen Amendment actually stopped the growth. It curtailed the production entirely of CFCs. And now this is what our future looks like. There have been other little amendments that have made it, brought things forward a little bit. So the Montreal Protocol, not only it had a scientific process to it, it has a multilateral fund to enable countries, but it's also an evolutionary agreement. It's allowed to change, to strengthen itself. And of course, if you find out that there's some CFC that is absolutely necessary, then it can be loosened a little bit. So it's a very practical, pragmatic document. So, okay, so I've told you we knew there was a lot of ozone depletion. The Montreal Protocol came along. It's been regulating these things. So where are we right now? So that's sort of the next thing. Let me talk about CFCs first. So this shows it's a bar chart. This shows 1996 and 2012 conditions for CFCs. This one down at the bottom, methyl chloride, is a natural compound. It's released naturally. So that's our natural CFC, or chlorofluoromethane, in the atmosphere. Here's CFC 12. Now this one has a lifetime of about 100 years. CFC 11 has a lifetime of about 50 years. And then the other gases here. This one up at the top, methylchloroform, only has a lifetime of 5 years. And it was regulated back in the 90s. So you can see methylchloroform is completely declined. Most of these other gases are still around, though. So we've dropped about, I measure in parts per trillion, about 312, about 9% decline of chlorine, mainly because of this decrease of methylchloroform. Now, I also talked about these halogenated compounds. This is methyl bromide. It's both natural and anthropogenic. And then these halons, which were used in fire extinguishers. And you can see that, in fact, they've dropped a little bit also, 2 parts per trillion, about 12%. And so things are getting better. We see the CFCs really are declining. So now what about global ozone? So global ozone, we measure it with these from satellites, with these ground instruments. And you can see, this is a chart in time, and this is percentage, okay? So it's the percent difference from what we were seeing back in this period. So you can see as CFCs were increasing, that the ozone was going down. There's a lot of year-to-year variation. Mount Pinatubo goes off, and Mount Pinatubo has a very interesting, when you inject particles into the stratosphere, they actually modify the chemistry. So we got a sharp decline for Mount Pinatubo. And you can see that CFCs are slowly starting to decrease now. And if you kind of, put your hand over the Mount Pinatubo spot, you can kind of see there's maybe a hint of a slow increase here. Remember, these CFCs have very long lifetimes. So this happened pretty quickly. This is going to recover fairly slowly. And I'll show you more about this in a little bit. But we're starting to see these hints that things are getting better for the ozone layer. We're not there yet. We're not back to where we were in the 1960s and 1970s. But we're on the right pathway. So what about the ozone hole? So there's the Farman points that I've already shown. And this is where we are up to the present. So the red points and these purple points are satellite observations. The black points, again, are the Halley base station data from right over Antarctica. And you can see that things declined. They were bad in the 90s. And now there's, if you look here, there's maybe a hint that things are on the upswing. A lot of this is just year-to-year variation of the Antarctic stratosphere. Weather patterns are different, and so you get some variations. But there's a hint here that maybe things are starting to go up. Here's our typical pictures of ozone, and you can see, you go back in 1979, it was a fairly weak ozone hole. Things had gone down a little bit, but it was fairly weak. And you can see the year 2000 was a pretty good ozone hole year. And then 12, 13, and 14, the last 3 years, a little bit smaller than this. So again, there's hints that things are getting better. Let me very briefly say something about the Arctic. So this is, what I've done is I've averaged over the polar cap. This is year running along the bottom. This is total ozone again. You can see my Dobson units here, 300 Dobson units, 400. Up in the Arctic, in the northern hemisphere, ozone is naturally higher. But you can see compared from these early years that, in fact, it's gone down, and there are much larger year-to-year variations. 2011 was a very surprising year. It was very cold over the Antarctic. You got way more of these polar stratospheric clouds were kind of the enablers of large depletions. So there are hints that things are getting better. Things are, you can absolutely say things are no longer getting any worse, and things are hinted at a little bit of improvement. So now let me say, I said that the depletion stopped. What if CFCs had kept going up? This is sort of the world avoided that we've been talking about. And that gets back to this scenario here. So this is where we're really headed, as long as countries continue to abide by the Montreal Protocol. And here's where things would have gone if it had been business as usual. And with the expansion of the Indian economies, the Chinese economies, you can imagine that the chlorofluorocarbon use for air conditioning, car air conditioning, refrigerators and so forth, that this really would have happened. So let's take a look at what that world looks like. So I'm going to show two plots. Again, here's total ozone down here. Blue is very low, red is very high. And it's actually, this is a model simulation. So this model, it fully represents the Earth's climate every year. It has greenhouse gases, it has ozone depleting substances and everything. And if you look here, you can see the year over here. Here's expected world, that black line. You can see that ozone is going up a little bit. And in the world avoided, it's going up a little faster. So up to 1993. You can see every year, you can see this little blue area pop up. That's the Antarctic ozone hole. You typically see very high values up here in the high northern. In the tropics, it's always low, by the way. Ozone is always pretty low in the tropics. So now you can see by the year 2005, you can see that the chlorine levels are much higher here, up to 10 parts per billion, about half of that there. So this is where the Montreal Protocol has kicked in. This one, it hasn't. And if you compare the two, you can see the ozone hole is much bigger. If you look up here now, by 2019, you'll see the blue area popping up. An Arctic ozone hole has started to form in the northern hemisphere. If you look fairly carefully, you can see, though, that it's much bluer in the mid-latitudes. This highs of ozone that you see in the mid-latitudes, down over Antarctica in the southern hemisphere, that's disappeared. It's not very strong anymore in the northern hemisphere. This is 2035, 2036. So you can see now that ozone is getting lower and lower and lower here, and it's actually staying fairly high over in this expected world there. And you can see it just keeps going up and up and up. And I end the simulation in 2065. One thing I should add about this is that ozone depleting substances like chlorofluorocarbons are also greenhouse gases. So this is not only is it very intense in UV, but it's a lot warmer also. You can see by the end, the natural level of chlorine in the atmosphere ought to be about 1 part per billion. So this is about 50 times the natural, 55 times the natural. This has actually sunk. It got up to about 4 parts per billion, and it's now come down because of the Montreal Protocol. And you can see the difference in these two worlds is very large. Storm tracks have changed in this world. The southern hemisphere has gone into, the southern hemisphere stratosphere has gone into a permanent winter condition by the end of this simulation. So it's always winter in the stratosphere. Ozone absorbs, it converts all that UV radiation into heat. And so you have to have some ozone up there to create the annual cycle in the southern stratosphere, and that disappears in this world. So just to give you some idea of ultraviolet, the UV index, I think you've all seen the UV index. It's reported almost every day. And so this is latitude from the southern hemisphere, from the South Pole all the way to the North Pole. Here's the equator. And remember, I remarked that the sun is directly overhead in the equatorial region, and ozone is a little bit lower, so you naturally have a higher UV index in the tropics. And for me, a guy like me, going outside in the tropics, and I've been down there a number of times on field missions and so forth, I go down there and 15 or 20 minutes in the sun, I'll get a perceptible burn, okay? That's with a normal UV index at Hawaii or so, somewhere around 12, 13, 14. So you can see this is the latitude of Washington, D.C. I put it on there, and here's 2015 right here, okay? And you can see that you've gone from somewhere around a UV index of 10 back in 1975 or so, and by the year 2015, we'd be somewhere up here around 12. So about a 20% increase. Now, as you keep going out, as CFCs keep increasing, you get out here to a UV index of around 30, okay? Now, what that means, and it was mentioned, I think, in the abstract, was that a guy like me, 15 to 20 minutes would give me a perceptible burn. In this, you're getting more than about 3 times that radiation. That cuts it down to about 5 minutes. So if I'm outside for 5 minutes, so you don't even, you walk a few hundred yards, that's 5 minutes out in the sun. That would give a person like me a perceptible burn. So things like skin cancer, cataracts, all of those unfortunate effects would increase quite dramatically in this world. It would be almost, at local noon, it would be almost impossible to be outside. So, let's answer the question, where are we going? Okay. So CFCs have been regulated. They ought to go down. I showed you that expected world, and things look pretty good, but there's some interesting things going on. So I'll go back to that, and you can see ozone depleting substances like chlorofluorocarbons keep going down. So I want to show you a little movie or another little animation here. Here's the observations in blue, and here's my model simulation. Same model that I used to do the world avoided. But I did two scenarios in here. One, I regulated greenhouse gases in this one, and ozone goes like that. In the other, I just let CO2 increase. Just let it keep increasing. And you can see that you actually overshoot the normal levels of ozone. You don't go back to this line. It keeps going up and up and up. So in an unregulated CO2 world, CO2 just keeps increasing, business as usual. Ozone will keep increasing, and we'll have more ozone in our atmosphere. Not sure what that is, but
Oh, it's not climbing. It could be. Nothing's.
well, yeah, they're really scared by this plot. So this is the expected. So we're going to wind up out here by the year 2100 with we'll either be near zero if some of these climate negotiations take hold, or we'll be up here around 6% above average if the climate negotiations don't take hold. Now that sounds like a good story, but in fact, it might not be. We don't know. There was a lot of research to look at how decreases of ozone impact things like plants and people. There have been much fewer studies looking at this end of what would happen. We do know that you do need a little bit of sunlight to get vitamin D production. So, you don't have to hide away from the sun. You need some vitamin D production. It doesn't take a lot of time. Particularly in winter, you should, pay some attention to taking vitamin D supplements and so forth because you can't get enough sun. But you do need, here we've got too much ozone. We may be screening too much UV, so we don't really know what that world is. What about the future of the Antarctic ozone hole? Well, I got to put a picture down here. And again, same model that I did the world avoided, but this one just has ozone recovering. And you can see, again, it drops. We produce a nice ozone hole. That's what it looks like. And it recovers. And so the ozone hole should be back to the 1980 level sometime around 2070. And it'll keep recovering as the CFCs disappear from our atmosphere. If you go back to the 1960 level, if you want to get back to the 1960s, then it's somewhere out in the 22nd century where you'll be back to the 1960 level. And because CFCs have long lifetimes. So now let me say something about what will happen in the future with refrigerants. So the Montreal Protocol regulated CFCs, which are used in our car air conditioners as foam blowing agents for insulation and for cups and so forth. And that was all eliminated. Okay, so what was it replaced with? Well, it turns out it was these emissions were projected to increase. Moline and Rowland were, and then there was an interim compound called a hydrogen chlorofluorocarbon. And the hydrogen atom attached to a CFC gave it a much shorter lifetime. And so it was much less effective at depleting ozone. And so all of the CFCs, which are the emissions, this shows emissions in megatons per year, they're being replaced by these HCFCs. But now those have also been regulated. And so they're going to be replaced with, a class of gases, hydrofluorocarbons. Now, they don't have a chlorine on them. So these hydrofluorocarbons don't destroy ozone. They're ozone friendly, perfectly ozone friendly. And so you can see the expansion of all these other economies now. There's going to be replacements in the US and Europe, expansion in other countries. There's going to be a lot of emissions or a lot of production and emissions of these HFC compounds. So the basic story of the Montreal Protocol is that the Montreal Protocol regulated CFCs. It brought in these interim compound, HCFCs, and the HCFCs are now being replaced by HFCs. And in fact, all of you have an HFC in your car air conditioner now, unless you've got something that was produced back in the 60s or 70s. So now you've all got a compound called HFC134A that's in your car air conditioner. That's what's used now. So it's one of these replacement compounds. It's already, you can see there's a little red here, it's already being used quite extensively. And let me show you something about the HFCs. This is one HFC, HFC23, and this is its global abundance or its global average abundance, and this is here. These are all observations, so you can see it's going up and up and up. Here's another set of HFCs. You know, every different sector, either for foam blowing or car air conditioner or a refrigerator or an air conditioner, they all use different combinations of these things. You can see here is 134A here. This is in your car air conditioner, and that's going up and up and up. And it will continue to go up. So they're all going up almost exponentially now. So these HFCs are all increasing. And they're increasing because of the Montreal Protocol. So that's sort of a good story. It's a great story for ozone, but it's not necessarily a good story. This is going back to emissions again. And this is emissions of in gigatons of carbon dioxide equivalent. Okay? So what I did is I took all these gases and I converted them into what if they were like carbon dioxide radiatively. Okay? How do you compare all these gases? So you can see here's the total. These are the CFCs. The CFCs were very important radiative gases. They were going to warm up the Earth. And actually, it was about, in that world avoided simulation I showed, it's about a 2 degree change, 2 degree Kelvin change, or about 4 degrees, 3.6, Fahrenheit. So it was actually a large global temperature change due to CFCs if you had not regulated them. Well, they've been regulated, and you can see the blue line, it's going down. So the CFCs are doing, the HFCs, they're the interim compounds, they're going to be regulated, but they're going up a little bit. The HFCs are all going up. Halons are about the same. Again, they have for long lifetimes. So you can see these gases now are all about equivalent. If I zoom in a little bit, you can see that a little bit better. HFCs, HCFCs, and CFCs in the year 2012 were about equivalent. Now in the year 2015, HFCs is probably up here somewhere. CFCs and HCFCs are probably about the same, and CFCs have continued to go down. So now really in radiative forcing, let's take a look at that. So this is what the Montreal did for surface radiative forcing. So this is how much energy is coming in, is remaining down at the Earth surface because of the presence of chlorofluorocarbons. So as they were building up, you're getting greater and greater radiative forcing. And because of the Montreal Protocol, they turned over and they're going to head downward. These are what the HFCs are going to do. So the HFCs are growing. They contribute, those are all greenhouse gases, all those HFCs that I showed you. So that everybody's got HFC 134A in their car air conditioner, which replaced a CFC, but it's actually a greenhouse gas. And so all of those HFCs are starting, and these are different scenarios. People use different economic models to project how far things are going to go up. And so how, you know, the expansion of different economies and so forth. So you get, I think these are the two best. So we're going to wind up somewhere between that here and here. And you'd have to add this purple and blue line to that black line to get everything to add up. So the total line actually kind of goes up like this, okay, as you add these two on top of the black line. So the bottom line is the regulation of CFCs was a great thing for climate because CFCs are powerful greenhouse gases. But by replacing them with HFCs, we retain the gains you made for ozone depletion, but you're losing the gains that you made for climate. So you made some great gains for climate because you got rid of CFCs. But now you've replaced it with a compound that are about equivalent for radiative forcing. So let me take it to a summary. And I'm basically going to tell you that the Montreal Protocol was a great success story. Okay? Chlorofluorocarbons were identified as a threat to the ozone layer, and the science since 1974 and the last 40 years has really nailed that science down very, very well. The early model I showed showing ozone being depleted from 1979, the new studies with new modern models, and these are three-dimensional global coupled climate, chemistry, ocean, atmosphere models. They're very complex models. They simulate their own different winters and everything. They really showed that there would have been a tremendous impact, really an existential threat if CFCs had never been regulated. And I mentioned a lot about the UV impacts on people, but the most profound effects would have been in terms of food security. That is, as you began to damage crops, we live in a world in which we can, barely feed everybody on the planet. If you were to drop the crop yields by 10 to 15%, then people somewhere would start to starve, okay? That creates political instability. Remember the riots that broke out in Tunisia was about food, okay? It started as food. That's what set off the Arab Spring. So food security is a huge issue. The first impact of ozone depletion would have been on food security. People can wear sunscreen, people can stay in more. You can't protect crops. So that would have been a pretty bad place to go. The really good story here is we're now in the science, the quality of our measurements is such that we're starting to see signs of improvement, which is great. So the Montreal Protocol, I talk about it saving the ozone layer, but it also really benefited climate change, a very important benefit for climate change. The increasing levels of the replacement compounds, the grandchildren, if you will, of the Montreal Protocol. If CFCs they're the grandparents, the children of the HCFCs, and the grandchildren of the HFCs. The growth of these HFCs may cancel the benefit gained by the Montreal Protocol. So, thank you for your attention.
Thank you very much, Dr. Newman. And we have time for a few questions.
Yeah.
A couple of why questions. The easy why is the Antarctic more sensitive to the impacts? And the second why question is why was there an ability to have a scientific and then a political consensus on CFCs while we haven't achieved that on CO2 and climate change?
Two great questions. Okay, so the first question is, why is the Antarctic more sensitive to ozone depletion than the Arctic? And the easy answer to that, well, it's not really an easy answer, but the basic answer is it's way colder over Antarctica than it is over the Arctic. And the reason it's way colder is because the southern hemisphere tends to be almost an ocean hemisphere. That is, there's not that much continental mass in the southern hemisphere. And so the troposphere, which drives a lot of the stratospheric circulation, there's less impact of the tropospheric circulation, weather patterns on the stratosphere. So it gets really cold over Antarctica in winter. That enables more of these polar stratospheric clouds, and they have you activate more chlorine, you get more ozone destruction. The northern hemisphere, it has the Himalayas, it has the Rockies, it has big continents, so it tends to drive very large-scale weather patterns that then in the troposphere that then impact the stratosphere, making the stratospheric Arctic region much warmer. So there are fewer PSCs, and there's less chlorine activation and less ozone destruction. But there are occasional years, like in 2011, where it did get really cold. So you have a lot of interannual variability, and you do get a lot of ozone depletion. So that's the basic answer about southern versus northern comparisons. The second question, and if I can paraphrase it, is why does the Montreal Protocol work and Kyoto doesn't? And the answer to that is actually fairly complex. But I will say that I think that there's an element of the right people at the right time, okay? And I think the Montreal Protocol did have that. The guy who signed the Montreal Protocol was Ronald Reagan, okay? The current crop of I think, of politicals would not have the nerve to do it. That's one. The second thing I think is that you had technologies in the mid-'80s that could enable the replacement of chlorofluorocarbons. And so there wasn't in every sector, there weren't replacements. For example, meter dose inhalers, the little asthmatic meter dose inhalers, used a CFC in a meter dose. They didn't have a replacement back in the mid-'80s, okay? But there was a lot of belief that, in fact, with the technology, with smart people looking at the problem, we could solve that problem. And so they moved forward, knowing that they had some technological solutions, and they could develop technological solutions. If companies know they're not going to have a particular chemical to use as a refrigerant in their car, they're going to go find something else that's both, safe, ozone friendly, and climate friendly. But they have to know that before they're going to start investing money in it. So I think that was one of the elements. But I think really people, the people at the time, worked hard on the problem. And there were some really key people that, maybe aren't there for climate negotiations. But climate negotiations is a really tough issue, and everybody drives cars. Everybody has everybody has, they use all their electronics at home. It makes it a lot harder to do climate than it was to do ozone depletion. Yeah.
Characterize them HFCs as being probably a problem for climate. Is anybody working on a grandchild, great-grandchild?
Well, that's another good question. And the answer to that is yes. Right now, there's been a lot of discussion over whether there ought to be an amendment to the Montreal Protocol that deals with HFCs. All the machinery for regulating chemicals is well embedded in the Montreal Protocol. The technology people who know all about refrigeration, foam blowing, meter dose inhalers, there's a huge range of technologies are embedded within the Montreal Protocol. And so if you wanted to do HFCs, you could do it under the Montreal Protocol. Now, HFCs are also included in the basket of gases under Kyoto. But under Kyoto, the big issue is about carbon dioxide. It's not about HFCs. So there's no energy really being expended in Kyoto to think about controlling HFCs. But there's been a lot of discussion, because it is the grandchild of the Montreal Protocol, what to do about HFCs. And within the Montreal Protocol, technically, the Montreal Protocol can regulate not only gases that deplete the ozone layer, but their replacements. Okay, so there is legally, the Montreal Protocol could do this, and technically they could do it. There's maybe a little bit of negotiation between the Kyoto Agreement and the Montreal Protocol to do this. It's really up to the 198 nations, though. The United States, Mexico, and Canada right now have a proposal before the Montreal Protocol that would regulate HFCs. So it's possible that it can happen. I don't know that it will happen. It's up to the these 198 countries. One thing I should remark is, I think you mentioned at the start, Stephanie, about the Montreal Protocol being a successful agreement. Every country in the world has signed the Montreal Protocol. There is no other agreement in which that's happened. So it's a remarkable agreement. And in fact, I attend, as I showed the picture, I attend these meetings at all time, and it's quite remarkable to sit with some really very smart people. They don't know a lot of the science, and that's okay. That's why I'm supposed to be there to talk to them about the science. But they're very, very smart, clever people, and I wouldn't be surprised if they did negotiate an HFC amendment. Yeah.
Dr. Newman, thank you so much for your talk. You've elaborated on how the people were instrumental to the success of the Montreal Protocol in comparison to the Kyoto Protocol. And you've also said that there's improvements and advancements technologically to have the great-grandchildren of HFCs. In your opinion, what else can we learn from the success of the Montreal Protocol that would help in climate change negotiations?
Well, I think it's a great question. The first lesson is that I think there's a lot of, in the climate negotiations, there's a lot of discussion about how it can never happen. But that was said back in 1981, 1982, 1983. It can never happen. I mean, there's evidence that every nation in the world can work together to identify a problem and solve it. That's the first thing. A lot of people said it's just not possible. Well, we have a glowing example that, in fact, it can be done. And so that's the first thing I always say is that if you go and you watch these meetings or attend these meetings, you're really encouraged that people can work together for a common problem. It's really kind of a nice thing to see. I mean, from my viewpoint scientifically, and I will admit to being kind of a crazy scientist, I love the idea of, scientists love extraordinary environmental events. That's where good science really comes out. So I tend to be a little bit neutral about the political side of things, because I'm really interested in, if a really good ozone hole pops up, it's really bad for people, but I find it to be very fascinating. Same thing with, hurricanes and other environmental phenomenon. But I think, you know, as far as the differences in people, you really do see that people can work together. And to me, that's really encouraging. I think in Kyoto, if some of the right people would pop up in the right spots, things could really happen.
Could you describe what the right person would be?
I don't know. It's got to be. It's a collection of people. And I remember back in the Montreal years, there were European nations who didn't want to regulate, and the right people popped up at the right time to look at the science, look at the policy. Same thing happened in the U.S. Richard Benedict, who is the lead negotiator, has written a nice little book about the Montreal Protocol. Was one of those people. But again, you know, Kyoto is a much tougher problem, and so you need, you know, much more. You need a lot more tougher, smart people to deal with the problem.
I think that concludes our lecture for today, and thank you so much for attending. And thank you, Dr. Newman.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.